Hello everyone, good afternoon. Welcome to today's webinar on Discover Everything from Composite Engineering to Manufacturing with a 3D Experience platform. This is Zainab Khalid, a marketing executive at LaunchTech, and I will be supporting you during the session. I would like to introduce our speaker for the day, Mr. Kiran Babu. Kiran is the industry process consultant for the SOS system at LaunchTech. He brings with him more than a decade of experience in consulting solutions for the aerospace and automotive industries verticals in the field of product design, digital manufacturing, composite engineering, and collaborative engineering. Before I hand it over to Kiran, I would like to remind you that on the top right of your screen, there is a tab for questions where you can ask questions and we will answer it at the end of the session. Also, next to it, there is some handouts that you can download to know more about the topic. Now I hand it over to Kiran to start this insightful session.
And good afternoon, everyone. My name is Kiran Babu. I am the industry process consultant for digital technologies from Dassault Systems from LaunchTech. I would like to thank each and every one of you for taking the time to attend this session. The session is roughly going to be for 40 minutes, and we would like to have a Q&A session towards the last 10 minutes. So without any further ado, let me get straight into it. So before we go ahead and see the entire range of composite engineering to all the way to manufacturing within the 3D Experience platform, it's very key to establish three components. The first being where are composites used. Um, so it's of no secret that the aerospace industry were the early adopters for composite material usage. The strength and power to weight characteristics were second to none. It reduced the overall weight, which resulted in better fuel economy and increased flight time. The automotive market has always looked up to the aerospace vertical for inspiration and guidance. For technology adoption, it was natural for the automotive market to pick up the usage of composite in commercial automobiles. Then these success and benefits gained over a period of time in both these fields, which is automotive and aerospace, fuel the adoption of composites in other diverse engineering and engineering verticals. So materials were adopted, composite materials of these kind, whether it could be for better thermal performance, it could be for better stringent environmental factors, started moving into other industry verticals such as the marine engineering, prosthetics, dental implants, and industrial equipment. So, hence, over a period of time, composite materials proved their versatility across various industries. So, before I go ahead, I have a poll for you just to understand the kind of attendees that we have today and your backgrounds. So, I'm going to give it a quick 2 minutes. Okay, pretty interesting. So looks like we have a good mix of aerospace and automotive industrial equipment. Fantastic. Let's move ahead. So the second being to establish ourselves on what composite materials are. Now, composite materials on to just understand the generically the term across different industry verticals is the same. Wherein when we define a composite material at an elemental level, it is made up of two constituents. One is what we call as a reinforcement fiber, which is basically going to ensure mechanical strength, and other being a matrix, which usually is a resin, which helps in the cohesive bonding of the structure. These two would result in what we call as a composite or a multi-layered material. Uh, Now, having this, we understood where it is used, we understood what it is. Now, let's quickly look at why it is being used and why such kind of big, large scale adoption under different industry verticals has happened. The first and foremost is when we look at design. especially when you look at the design of automotives and aircrafts and automotives, you look at a lot of functionalities because we are supposed to train engineers to think in three verticals, which is fit, form, and function. With composite, what happens is it's easier to enable complex shapes to be manufactured because entirety of the process and the way the material behaves enables designers to think complex shapes and ultimately produce these complex shapes. Now, the other advantage that it brings is, of course, the composite material gives you a better power to weight and strength to weight ratio, which helps you to design more stiffer and high performance entity and materials for the same application. So that's giving you reduction in the weight. The other is, again, from a manufacturing point of view, is basically you're having fewer assemblies because you're making more bonded joints rather than going ahead and having individual pieces together, stitched together with fasteners or with adhesions. So that's the other advantage that you get. Then from a manufacturing view, you understand, yes, the tooling is less complex. I'm sorry, it's less costly because once you have a tool, you understand that it's a combination of different parts together. But with the production processes that we follow, it becomes to have some standard templates that you can work with. So just to reiterate, you from a designer's point of view, we can achieve complex shapes. From a validation point of view, we are having to work with the material. Inherent capability is of having lesser weight, that is better weight to strength ratio. And from a manufacturing or a project producibility point, we have looking at assemblies with fewer parts to assemble because we can have one cohesive monolithic structure and then lower cost in the tooling. The last but not the least is the we have looking at materials which are inherent to the process of having less corrosive behavior. So composite technology and challenges. So when we look at parameters of from a material standpoint, from a composite material standpoint, the few of the key parameters are the parameters in terms of material properties, that is in terms of how the material is carbon fiber, or we are looking at Kevlar. So it brings its own inherent different material properties. Then the laminate structure. The laminate definition could be in terms of a pack of plies where we are trying to define the fiber orientation and stacking. Now, even though this is a complex material to handle, now what happens at time to time is we are going to work with multiple design changes because now the question comes is when we are going to change the design, it's of course going to consider different material characteristic, material behavior, and overall size of the part. So when we look from a designer's point of view, again, it's very much inherent and very much important for us to make sure that the design that we come up or the resultant design is going to be estimated weight. That is, we are arriving at the estimated weight. We are looking at that structural performance of the part, is making sure that the part that we design or intend to be manufactured is going to perform as it is or as intended. And then also the other part of it is when we design these structures, you have to make sure that along with the design implications, you're able to create downstream manufacturing applications or downstream manufacturing documentations, which can be templatized and also streamline the production process. So this is from a material point of view in terms of production, in terms of design. But now let's look at it from an industry point of view. Let's look at it from an aerospace point of view here. The first challenge is in the aerospace industry, we are today looking at smarter composites. What do I mean by this is if you look at the technology adoption or the material adoption in the aerospace industry, you can see a few numbers here on the bottom right where it says that there's an increase of composite usage in aircraft, especially in the Boeing 787, the Dreamliner series. That's around 50% of the structural parts are made up of composite fiber. Similarly, in Airbus 350, the wide body product portfolio of theirs, there's again an adoption of 50 to 60. So there is a steep increase in aerospace OEMs adopting composites as a material of choice for building their structures and the overall aircraft. Now, what does this bring? This brings its own challenges because when we are looking at adoption of material, we are looking at a key capability that the material can deliver. So for in this case, we are looking at an advantage over the material counterparts to see in terms of conductivity, in terms of toxicity, I'm sorry, and also the mechanical behavior prediction. We are also having composite parts in which between the layers or between the layups, we are able to embed sensors to understand the cracks, the thermal deviation, so on and so forth. We're also having developing new paint coats which are adherent onto the surfaces of these composite materials. We're also developing morphed actuators, very much used in the aerospace industry for their control surfaces. So this being the need of industrial designers, this being need of the aerospace designers to adopt these technological advancements on these materials. So they're looking at not just replacing the metallic parts, but also that trying to initiate to use that material characteristic to achieve these different goals as well. The other challenge of the industry, particularly from the aerospace again, is of course looking at cheaper composites. So how do you make it cheap? It's purely on how what's the volume of production that you can bring, the reduction of resources required for producing that part. So if you look at it, it's become more automated, it's become more versatile. The part sizes have increased considerably. The production rate has also gone up, and the tooling complexity. Now, this is a very key factor because the tooling complexity itself, since you're making single frames and single monolithic structures, it's become more complex in terms of it's becoming more demanding for tool makers to bring out those kind of tools in terms of fixtures or in terms of the actual mold surfaces itself to make it as get it right the first time. The fourth is the constant. I would say this is the constant behavior of aerospace designers, where they want to reduce the number of fasteners, reduce the number of these joiners. So this has become inherited because these materials can deliver. The other area of it is on how do you get a well validated result. Now when I say well validated result, it's of two types. One is you're simulating in terms of performance, right? That is the actual performance, the fit form function. The other being the fact that we are looking at the robustness. So once we have something that is designed, basically an aerospace part that has been designed, we're trying to stick to understanding the form, fit, and function. So the next is basically the errors on the shop floor. Very inherent situation here is this is something which leads to complex rework, very pricey reworks. Reason is whenever we have these kind of issues and repairs on the shop floor, it's kind of an extra added resource in order to correct that function. So how do you catch hold of those problems? And the other part of it is the actual production. So now with the technologies aggressively moving towards automated fiber placement, you need to have a technology that helps you to design, validate it in terms of multiphysics, and then also having a coherent solution which can push this information to machines to actually go ahead and fabricate the part as well. So this is from an aerospace point of view. The other industry, which is again using composites on a large scale, is again the wind energy industry. Here, more or less the same kind of challenges, but there are certain differences because here the question is how do I ensure that it's manufactured in the right way, the design that I have is repeatable, and also to make sure that the design is optimized for RTM. RTM here stands for resin transfusion method, which is basically kind of a process that you use for manufacturing composites. So how do you create a design which is optimized for that process? Um, how do you make sure that the information flow directly from the design shop to all design floor to all the way to the shop floor is seamlessly communicated? How do you make sure that maintenance is reduced? Now this is something which is very important in the industry because we are looking at windmill blades which are facing erosion factors. So how do we delay the erosion? How do we make sure that the planned maintenance time is also reduced? So how do you build a structure that can enable you to take all these as your consideration? Now, moving forward, we can also look at the other industry, which is automotive. Different ball game altogether, because in automotive we are looking at how can we quickly mass produce a particular item or a particular product, at the highest efficiency possible with the highest amount of complexity in its surfaces, and to make sure that you are able to track each and every model's performance as it's being innovated. It's a very demanding environment as well, from a design as well as from a production front, is because here you can use resources which are automated. You can have combination with manual resources used for producing the part. So, and before we all talk about production, it's very, very important that the CAD element that has been revised, reiterated, is run through its simulation cycle to understand if it fits and checks boxes all the simulation checks that you would like to run on the material. And ultimately, the once there is an approval on the simulation, ultimately it comes to the fact that we need to make sure those information is available for the shop floor. So do we have a convenient medium which can enable us to have design sorted, and then from there take that design and do multi-physics simulation on it, be considerably understandable that okay, these are the products and it's going to deliver its function. And once that is done, can that same system allow you to go ahead and create downstream materials, downstream manufacturing documentations? So different industries come up with different challenges. The way we at Dassault Systems and Launchtech, we look at this problem is we break it down. So in a traditional approach, we actually start with understanding it from a virtual standpoint. That, of course, is to understand the information that we have collected. It could be a solid phase, it could be a monolithic solid, and from on that monolithic solid, we would try to recreate those different entities to enable the information of composites. We would bring that to a CAD platform. In the CAD platform, you will start to lay up all these informations in terms of the material, in terms of the fiber orientation, so on and so forth. And then again, you push it to another entity for simulation. You do a multi-physics validation there, and then push it to another system for production. Now, when we do this, this is an iterative process. So there's always going to be a loop back to each of the systems to optimize and check and validate, and then push it back to the production environment. So there's going to be a loop system in the sense that it's going to be an iterative process. So when this happens, as you see, if you're going to work in this kind of environment, naturally what happens is you're going to have a lot of translation of data that's going to happen. There's a lot of information loss that could happen when you're translating information. And designers have to figure out every single time the data, once it comes from one system to another, not just designers, it could be simulation designers, manufacturing engineers, who are working part of the system to understand that, okay, the information that I've received, is the data perfect? Is it intact? Does it have all the information that I require? So it's every time that check has to be done and it has to be streamlined. So what we look at in Dassault Systems is to make sure that we have this entire ecosystem tightly connected and integrated with the best tools that offer its own capabilities in each of these different segments. So starting from composite design all the way to simulation to manufacturing, and then extending that environment across to different partners who could be in taking care of nesting, or you could have tape layup, or you could have resin transfer molding. So it's basically creating an ecosystem that is scalable and extendable to other entities as well. So how do we do this? So let's start with the first piece. The first piece is the composite design. Now, in the composite design, there are basically three methods that we follow. The three methods are zone and grid approach, solid slicing approach, and Excel sheet approach. Now, question can be asked, why three approaches? Each of these approaches have their own substantial benefits. Each of these approach has to be carefully considered for the product that you're trying to manufacture. So let's say if you're looking at something very simple, uh, and you want to go ahead and use a ply by ply approach to do the layup, you would actually use what we call as the first zone and grid method. So it would look something like this. So in this video, what you'll be able to see is the fact that once we go ahead and set up on the system, we have your the mold surface to work with, in fact. And from there, what we'll be able to do is we'll be able to create wireframes. And on those wireframes, we'll be use them as markers. And for those markers, we are actually going to go ahead and populate those markers, that is basically the regions or the contour, with ply groups. Now, this is where we'll be able to go ahead and define different wireframes to make sure that we have a contour correctly selected. We have different tools to go ahead and select the right material, the right orientation. And once we do that, we can go ahead and, of course, we can populate them with more plies based on the orientation that you would like to achieve. Now, as we keep going ahead here, the significant thing is you have tools dedicated for each process, each stages of the process. So that could be the fact that what you're seeing here right now is what we call the ply table, which gives you the complete control of all the ply stack up that you have. You can go ahead and change its name in terms of its series. You can change the material, the orientation, the sequence, basically the entire stacking. So this gives you a complete control of them on an Excel based in an Excel based outlook here. So this is very important because this helps you to go ahead and push this information into an Excel sheet, which you can later use for simulation as well. Once we have done the composite deck, we can go ahead and use tools here. What you're seeing right now is exploded plies. This shows you the different layers of plies that you've applied. And you can use tools where you can, on the fly, you can go ahead and, not even click on the part. You can just hover over the part and it's going to show you information in terms of the ply ID, the material, the orientation, the sequence that it is in. So this is a generation of how we are able to achieve this on a simple part with a simple ply by ply approach. Moving forward. So let's look at something called as zone design, which again is used for more complex systems and complex shapes. So in zone design, you can see the workflow here. What we do is over there, we had defined ply groups. Here, we're going to define zone groups. So zone groups is basically going to define an area on the oval surface, and in that given predicament area we're going to go ahead and populate with the ply information, so something like this. So here what we will be doing is we will be capturing that area. When I say area is defined based on the wireframe that you draw on the surface. Once we define that area on the surface, we'll be able to capture that information in terms of what are the laminates that's to be populated in that region. So it would look something like this. In the same context, we are defining the zone group, and for that zone group, we are defining different laminates. Now, these laminates can be a predetermined set of information that you can pull in from an Excel, or you can configure them within the system itself and create a data bank out of it, and then call that data bank whenever you require. So here, what I'm doing is I'm uh, defining the area in terms of the contour or in terms of the zone, and for each of this zone, what I'm going to do is I'm going to define the ply group. Once I've defined the ply group and the staggering value, I can also go ahead and automate and check what would be my final output solid, just to give a reference of how the part would look when it's getting manufactured. We have the solid slicing method. This method is explicitly used for, again, for monolithic parts, but in the aspect that, for example, let's say you are looking at uh, you're looking at doing a composite part for a stator blade in a gas turbine engine. This is the methodology that would you use. So the second, the fourth, and the most important one is called the grid-based design. So in the grid-based design, this is for handling complex assemblies. It's handled in a way where we actually define a grid panel, and for that grid panel, we'll be able to populate the ply information. So it's going to look something like this. So here what I've done is I've taken an aircraft skin. The aircraft frame has certain structural frames, and then they have the longerons, the stringers. And what I'm going to do is I'm going to use those structural frames. Okay, I'm going to use those structural frames and then go ahead and use those frames to define what we call as a grid. So in this grid, we will be talking about each of these panels, and in the grid, we'll be able to go ahead and populate the different kinds of zones present in those grids and populate them with information. This information can come in from Excel sheets. It can come in from different sequences that you're pulled in from an Excel. So here what we can do is we can go ahead and create symmetry. We can do resequencing, sequence the entire structure of the plies. So then this particular approach is again dedicated to an Excel sheet approach wherein we can pull in information directly from an Excel and put it onto the CAD surface itself. So a complex set of solutions are available for defining different composite design for different structures. Now, in terms of simulation, before I go ahead, I'm going to give you a quick poll. Okay, thank you for the answer. So there's a good mix of information here. So we have a good mix of good mix of attendees here. So in terms of simulation, you need to understand that the same interface where we're going to go ahead and design the 3D CAD model, then we're going to go ahead and submit each of the zones that's going to be present, basically declaration of the wireframes. We're able to go ahead and give information of each of the sections, then do the meshing, and then run the analysis. All of this is done in the single interface, which is then powerful. It's not just running them in a single interface, it's also the fact that we are also having geometry related optimization, which is basically to re and defeature those features that is not required for you while you're doing your modeling for meshing. So we have those dedicated tools as well. The rest is again in terms of creating properties. These properties are created in different zone methods. So in each of these methods that you have captured, the FEA properties can be directly translated into your simulation, and those simulation can take those properties and run the simulation type that you require. Now, the simulation that we run has a different methodology as well, called as rule-based method, in which we'll be able to go ahead and create different rules which will help you to templatize a standard structure for operation, and also to keep that template for similar kind of parts in the future. So we have a high performance in post-processing, which helps you to visualize common failures in terms of psi wool uh, and psi hill, the maximum stress and the maximum strain, and then different damage variables coming in from hash and damage, and the different types of evolution. So here you can see that you can go ahead and understand the worst case scenario here. What is the worst ply? And for that worst ply, where is the structural damage that occurs? So the post processing also happens quickly on the same interface. We also have another, apart from the pre-processing, we also have tools which will help you to go ahead and automate the process. So this is a significant leap, because here the automation can run in simpler loops, or you can have situations wherein you can have adapters which comes from another line of system, can push in the information and run its loop in terms of optimization and get back to the result. So you can keep on, so it could be as simple as possible or as complex as you want it to be. So this is a simple example here. What you're seeing is a winglet, and in the winglet, uh, you have the process optimization that is being created in the middle, and then the information is in terms of the stresses and strain that is coming from aerodynamic conditions, and then it's trying to optimize the CAD model by itself. Apart from this, we are also looking at different failure models, of course. So the failure models here are explicit analysis handled by Simulia Bacchus. That's our solution front, which solves explicit analysis kind of problems, wherein we are looking at two failure methods, which is one is for failure in individual plies, and then being the other for the delamination. We also have a technology called a C zone. This is to understand, and this is to basically to understand the crush factor in these composites under the loading conditions. For example, just to give you a quick idea here, what you're seeing on the right here is it's to understand the damage criterion for the reinforced composites under the Hessian theory. So could be a rupture of the fiber in tension. You can look at buckling and kinking and compression, and different matrix crushing under transverse compression as well. So we are also effectively looking at crack propagation. So this crack propagation could be a resultant of a simulation that you have done and then to variables, or you can initiate. So it could be either solution dependent, or it could be something on the fact that you're creating the crack along an arbitrary system. And of course, one of the most important topics here, which would be of to understand the adhesive layer. So Abacus allows you to detailedly model these kind of environments to understand the adhesive connections and specify the material that you want to control the connection in terms of whether it's finite thickness or the thin frames as well. So here we can study both adhesive joints and delamination as well. So in the delamination modeling, we are looking at, obviously about the cohesive behavior of the different structure. What you're seeing on the right here is basically the structure that is under delamination under a force implicit on the structure. So it could be both in terms of separation between layers, or you have a force induced delamination as well. So this is what you're seeing on the right is basically a crush stress. Now, the reason why we involve this, it could be a simulation factor that can run parallel to your ongoing simulations for strength, but it would also be something that can be done complementary to this as well. So here you can see there is a video that shows that the actual crush, and what you're seeing on top is what has been simulated on the software. So we are able to get those results and understand the peak fracture point of the crush test that's been committed. So the accuracy of that would be substantial based on the inputs that you give, of course. But here, what we're able to capture here is the basically this fracture peak that happens at a particular section and that beam. The other area of simulation would be the composite simulation for draping. Draping is a process where you have to use to go ahead and understand for a flat patterned composite ply, how do you drape over a mold surface. Now, the idea here is to understand the optimum blank, the optimum ply size and shape, to understand that if you're able to capture wrinkling while you're wrapping around different complex surfaces. It's not just that, it's also to understand the strains and stresses along weft and wrap direction of the fiber cloth, and to see where stretching or pre-stretch has to be done as well. So that's about what we are able to deliver in terms of composite simulation. Now, in terms of composite manufacturing, before I go ahead, I'm going to give you a quick poll to see what tools are being used and what are the different type of processes that you use for your composite manufacturing. Let me go ahead and take a quick look at the results here. Oh, fantastic. So there's again a good mix of strategies here. Um, so, of course, let's take a look at what we offer for these strategies. So, um, just right off the bat, since we have the entire design decked, we know the plies, we know the orientations, we know the stacking sequence, we have validated the physics in terms of the structure, in terms of obviously of how it's going to perform, the form, fit, and function, of course. Now comes the place where we are actually pushing off this information to manufacturing engineers. So here, the first thing that we do is what we call is dynamic draping. This is basically to identify the seed point. Basically, seed point is the first point of contact between the cloth fiber and the mold surface to understand the optimum position for the complete coverage, and obviously less stretch. So here, what you're seeing on the right is what we call is dynamic draping, is basically using the seed point to understand that from a given position, how much of cloth is going to cover, how much is going to be stretched, is the cloth going to be enough, those kind of considerations. And what you're also seeing is simultaneously, it's also generating the flat pattern for that ply as well. So this is another approach. We have also added, I would like to say this has been an added functionality, and it was a requested functionality from both Airbus and Boeing, wherein we are trying to, the flat pattern that is getting generated once we do these optimization cycle, we're trying to make sure that those plies have flies, those complete contours are being cleaned for different bumps and hollow, uh, you know, creaks and hollows that is available on the actual part. So the optimized information is available for you when you're going to construct a flattened ply. So if you look at the complete manufacturing process, once you have the information validated from simulation, it's going to be a producibility analysis, okay, where we run to understand how the cloth fiber is going to behave when you're going to lay it up, where there's going to be wrinkling. If there's going to be wrinkling, what kind of darts I need to use to avoid this kind of wrinkling? What type of stretch are we talking about? Is the material width going to be sufficient for that particular layup. Then comes obviously the next is would be the splicing it into cut pieces. From there, we can look at going ahead and flattening these contours because these flattened plies. Once these contours are flattened, we'll be able to go ahead and export this information in various formats like STEP, IGS, DXF, so on. Once that is exported, we are also simultaneously able to create one of the most important documentation for shop floor operators and laymen and engineers is the ply book. So this can be simultaneously created. So all the way from producibility analysis to splicing to flattening to creating the ply book can be done in a single UI. Now, this is just to give you a quick inference on how the system would look. So once we have gone ahead and run our simulation, this is basically a producibility simulation to understand if there's going to be any fiber deviation. I'm doing it for two plies here. I'm going and understanding right now that the material width is not enough. So I can go ahead and then add on to the next process, which would be going ahead and flattening these plies. So these are my splicing curves. I can use these curves to go ahead and splice my plies. Now, of course, I can rerun the optimization or the producibility analysis again for these spliced curves as well. So here we'll be going ahead now selecting what we call as a seed point to see that for a given guide curve and given location, are we having any kind of wrinkling? Are we having any kind of lift off from the surface? Is the coverage good for that particular ply? So this is me doing the producibility analysis. Moving forward, here is where we're going to go ahead and creating all the flattened plies for the ply group that we have selected. This would flatten all your plies, and then from there you'll be able to go ahead and create the flat pattern, of course, and then go ahead and generate IGs in step, which can be then exported into other native environments for production. So here what we are seeing is the automated generation of the ply book. The ply book is again an information in terms of giving you what is the right sequence, what is the thickness, what's the overall shape of the part, what ply to apply where, so on and so forth. So this is basically how the plywood would look. So here is a detailed drawing. So this is just to show you the automated process for creating the ply book. So once I have the views preset, once I have presetted those views, I can use a macro, default macro that's available to run the sequence and then create a ply book for the sequence of the order of the sequence that we have created while developing the CAD model. We also extend this capability to other manufacturing processes like composite braiding. Now, composite braiding is a process where we can go ahead and use what we're seeing on the right here, a robotic arm as a mandrel, and then go ahead and loop these seams on top of this particular metal bracket that you can use as a guide. So here we are able to simulate different simulations in terms of optimization and the mantle generation. Just to give you a quick view here, this is how it would look. So here we are automating the robotic arm as well to in tandem with the process of the wound. So we can have the complete mockup, and then we can have the entire tool part to be generated in terms to see if the layup is good. So here what we're doing is we are going ahead and declaring the composite parameters and plies, and then we can then run a producibility for braiding explicitly and understand the coverage. This extends to even composite forming. Composite forming is another process for the process of manufacturing. We support this fully integrated from the CAD all the way to the die machining and all the way to the robotic sequence as well. We extend this also to composite laser layup. This is the methodology that is used to lay up the composites on a given tool bed where you have different positions of lasers. We have the innate capability to develop what we call as .cal and .ply, which is for developing the orientation of these different laser pointers, and also the the dot ply, which is required for understanding the ply ID, or the kind of ply, the shape, the material, the fiber orientation, so on. So as I told you, there are different integration partners that we work with. The one for automated fiber placements, we work with Coriolis, we work with Ingersoll Rand. So the data is natively can be created within the environment and then pushed on to these kind of systems from these makers. So this is for automated fiber placement. Then we have for nesting. So this is basically we are able to export DXF and DWG files to these systems to go ahead and nest these different fiber sequences for getting them cut out of the fiber cloth as well. These are a few references that we have from the automotive sector. Very close to my heart is this, which is the BMW i3. The complete monocoque was designed with composites. The entirety of it was completely custom created within the CAD solution. Not just CAD solution, but they have used both the solutions from Dassault system for CAD as well as the CE for composite design all the way to simulation. Then from the aerospace, you can see all the big names here, which is Boeing, Airbus. Boeing for the 787 Dreamliner, the complete DMU mockup, starting from the CAD, the CAE to the manufacturing, the entirety of the process and workflow management was done within Dassault System Solutions. GK Aerospace to the right is a tier one supplier of aerospace products. They have used the entire solutions for not just for CAD, not only for producibility analysis, but also to simulate and validate these functionalities. As I told you, wind power is another major area where they use extensively composites. We have integrated ourselves with the top players, one being Ganesha, then you can see GE and LM. One of the most interesting takeaways here is the work with Ganesha, because the Excel sheet approach, the methodologies which I talked about in the beginning, was explicitly developed for these kind of applications. And this was done in tandem with one of the leading players, which is Ganesha here. Ladies and gentlemen, thank you so much. That brings me to the end of my session. I'm open to take questions.
Thank you very much, Kiran. Let me remind you, everyone, again that in the top right of your screen, you can find the question tab where you can ask questions. For the first question, they're asking Kiran, can we
Okay.
create, validate, and generate manufacturing documentation in single environment?
Of course, this is a definite yes. We can not only create the CAD model, we can not only simulate the CAD model with the composite deck, but of course we can also create the manufacturing deck, the end to end. So it could be the mold, it could be the mold surface, it could be the plybook that you would like to generate, or any of the other export formats which is required for maybe for nesting or for another system which takes care of resin transfer method as well. So the answer is a definite yes.
Okay, there is another question. It says that can productibility analysis be extended to curing process and strengths validation after curing?
Yes, we have. Like I said, we once we have these models, that's the DMA model that is being created. We also have a partner ecosystem that can help us to extend that capability to understand once the product is being cured, what is the deformation that that occurs to the product typically. So that would require us to extend our data into these partner streams or partner solutions. But the answer to is yes, we can definitely handle them.
Okay, another question. Are these tools available on cloud or on premise?
Fantastic question. So um, this is a question depending on what your business process. So if the answer to it is again yes, so it depends upon what kind of business process that you run. Based on that, these tools, all the capabilities, CAD, CE, and the manufacturing capabilities are available on both cloud as well as on premise.
Okay, another question. Is the CAD environment scalable? For example, can I add reverse engineering into existing workflow? And do you have tools for the same?
So yes, definitely the CAD environment is scalable. So we can add components such as reverse engineering to it. We can add composites such as mechanical design to it. to the existing workflow that you would like. So, for example, if you're deploying this product purchase for composite design, we can obviously involve or add applications for reverse engineering and mechanical design as well.
Yes, there is another question. Why it is not possible to edit evolution if effectivity on MBOM items unless all model versions are set to in work?
Interesting enough, this looks like to be a PLM side of things. Once we have defined all model versions and once we have defined the work in progress, you should be able to go ahead and transfer the elements from EBOM to MBOM. But again, depends upon the life cycle that you have classified, the kind of business process that you've done. So once we have it in MBOM, we can handle the complete end-to-end evolution of the MBOM. It should not be a problem. But it again depends upon the kind of the business process that you would like to achieve.
So thank you everyone for watching, and thank you Kiran for this insightful session. We hope you get all of you insightful information, and to be updated about our upcoming webinars, you can follow us on LinkedIn. You can also visit our YouTube page and website to contact us directly. And thank you again for attending. Have a nice day.